Thanks for that very kind introduction. It's a delight to be here, and especially I've had a wonderful month here already. This was my first month of my Hagler Fellowship, thanks to Bronnie and others here who helped make that happen. It's a great month, but sadly I'm leaving tomorrow morning, but I will be back for 3 months in the spring, and we'll have a lot more fun then. So this talk came about because because of an article written by Deb Basu called Learning Statistics from Counterexamples. And this particular article was about ancillary statistics. This says here Basu 2011, but this was just a volume of his collected papers. And I think the original article was probably 60 years old. So it was written a long time ago. In any case, there was recently a volume in Sankhya honoring Basu. And I was asked to write a paper on it. And I decided I really loved this article, Learning Statistics from Counterexamples by Deb. And so I said, I'll write an article with that title. And so it was called Learning Statistics from Counterexamples. There are 22 counterexamples in that paper that I think contribute a lot to understanding statistics. I'm going to talk about 9 of them in this talk. And the 9 I picked are the ones that I think are more influential towards thinking about one's statistical philosophy. And in fact, they're counterexamples that in some sense had a profound effect on statistics. I probably won't get through all 9. And also, so this is like 9 separate talks. And so, when I finish a counterexample, if you want to ask a question, go ahead and ask it. It doesn't make sense to wait until the end after I've gone through all 9. So first, let me start with just an ancillary counterexample from Basu. It's very simple. You have n bivariate normal observations with mean 0, variance is 1, and correlation rho, which is the parameter of interest. Now, if you look at just the vector of x's, and you look at their marginal distribution, they're just normals, they're just independent normal 0, 1 random variables. Doesn't depend on rho. Likewise, the vector of y's are normal 0, 1 random variables, and their distribution does not depend on rho. They are thus what is called an ancillary statistic. An ancillary statistic's definition is it's a statistic whose distribution does not depend on the parameter of interest. So the ancillary method in statistics says you should condition on an ancillary statistic and then analyze the remaining data from the conditional distribution. Okay, now if we condition on x, then it's easy to see that the yi are independently normal with mean rho xi and variance 1 minus rho squared. So a reasonable estimate for rho might be the sum of xi yi over the sum of xi squared. You can show that it's unbiased. The expected value of this quantity is equal to rho. Conditioning on y instead leads to a similar estimate, but instead of sum of xi squared in the denominator, you have sum of yi squared. So this example was just created by Basu to very simply show that ancillarity does not always lead to a unique answer. Further, these estimates are probably suboptimal. I mean, most inference about rho in this situation is based on the sample correlation defined there as R. I don't know if this is ancillary, this can be derived from some other ancillary statistic or not. I kind of doubt it, but I didn't really look into it. In any case, the background of this paper and why I think it's important for philosophy of statistics is that back in, well, so the conclusion is that one cannot build a complete theory of statistical inference or even an approximate theory based on conditioning on ancillary statistics. Now today, nobody would even have thought of that. But back when Basu wrote this 60, 70 years ago, there were many, many people working on ancillarity. And I talked to some of them who said, yeah, we can make ancillarity the foundation of statistics. And Basu just said, nope, can't. Here's a simple example to show why you can't. Okay. So the greatest counterexample in statistics is the likelihood principle. Alan Birnbaum wrote the famous paper on this. Alan was a frequentist, but in his 1962 paper, he proved that the likelihood principle followed from two other principles, and I'll go into that. And then in such a way that it kind of invalidated frequentist statistics. So this was an incredibly influential paper. Well, let's go through where it came from. So frequentist statistics in 1961, there had been extensive criticism of it by Bayesians, such as Jeffreys, Savage, Good, and Lindley, but they were mostly focusing on particular frequentist procedures and saying, look, there's something funny about this procedure. And here's a Bayesian one that looks like it does better. At the time, there were two core components of frequentist theory. There were more than these, but these two were part of it. One, the sufficiency principle, which everybody kind of agrees with, and two, the conditionality principle, as in the following variant of an example of David Cox. So an employee walks into work each day to perform assays and is randomly given either a new measuring instrument, which has variance 1, or an old measuring instrument that has variance 3. Now, conditional inference here would be to say for each measurement, report variance 1 or 3, depending on which measuring instrument you've been handed. You know, one of them looks old, one of them looks new. You could also do an unconditional inference. You could say, I get the new one half the time and the old one half the time. So over the whole day, my average variance is 1/2 times 1. Well, not over the whole day because you get 1 for a whole day, but over your whole work life, your average variance will be 1/2 times 1 plus 1/2 times 3, which is 2. So the unconditional inference says report a variance of 2, regardless of the instrument you're handed. Now, virtually everybody says that's ridiculous. Obviously, you should just use the conditional inference rather than the unconditional. And the condition, that's just what the conditionality principle states. And basically, it's just stated in this sense. I mean, you can generalize it, but just stating it in terms of this example is enough for what Birnbaum proved. Okay, now the likelihood principle. Let's focus on the likelihood function. So we have the density F of the data X given a parameter theta, the unknown. But we plug in the observed data. We plug in the observed data X, and what we're left with is a function of theta. The likelihood principle says all the information about theta obtainable from an experiment is contained in this function for the observed data. I mean, a frequentist would say, sure, all of the information is contained in this function, but it's for all data, and there'd be some kind of average over the data. So the likelihood principle precludes frequentist averaging over X, which is why it was, well, it probably is still contentious, I don't know. And then another part of the likelihood principle says that two likelihood functions, L1 and L2, contain the same information about theta if they are proportional. Now, what Birnbaum, so in 1961, virtually all frequentists viewed the likelihood principle as being wrong, and virtually all frequentists viewed the sufficiency and conditionality principles as being right. Then Birnbaum nastily proved that the likelihood principle is a logical consequence of sufficiency and conditionality. So the common view could not be sustained. Something had to go. Now, there's huge discussions following this proof by Birnbaum of the likelihood principle. Almost nobody was willing to give up sufficiency, but a lot of people who wanted to stay frequentists kind of argued that the conditionality principle can't be always applied. It can be applied sometimes, like here, but it can't be applied other times, like the way Birnbaum tried to apply it. Even though Birnbaum's application was mathematically equivalent to this, still that was sort of a way some people tried to escape from the conundrum. Uh, Another way was to, there were thousands of articles written about disproving the likelihood principle, but they were all wrong. They still continue to be written these days. And another way out was to give up being a frequentist. And quite a few people, because of this, switched over to either what is called the likelihood school of statistics or the Bayesian school, because both the likelihood school and the Bayesian school follow the likelihood principle. So this single paper, I think, had the biggest impact on statistical philosophy of anything. The likelihood principle is actually older than Birnbaum. It's probably 10 or 15 years older. And it's interesting to know where the principle came from. And so here's an example. Imagine two scientists are collaborating on an experiment. They have a joint graduate student who's conducting the experiment, and they're both watching her collect the observations. The observations come in, and they're Bernoulli theta random variables. We're trying to test theta equal 0.5 versus theta bigger than 0.5. They're watching the grad student collect the observations, and after the 9th observation, they simultaneously say, okay, that's enough data. We can go off and analyze and make our conclusions. The data consisted of 9 successes and 3 failures. So each scientist then went off and analyzed the data. When they got back together, they're shocked that they disagree. Scientist 1 claims that there is not significant evidence at the 0.05 level, where scientist 2 says there is. What happened? Well, scientist 1's analysis, he had planned from the beginning to take just 12 observations. Thus, for him, the number of successes X was binomial 12 theta. And if you compute the p-value corresponding to 9 observations, it'd be the tail area, X greater than or equal to 9, that probability given the null hypothesis, and it turns out to be 0.07, which is not significant at the 0.05 level. Scientist 2, she had planned to continue taking observations until observing 3 failures. So for her, X was a negative binomial distribution with parameters 3 and theta. And if you compute the p-value for that distribution, you get 0.0338, which is significant. Now, note that these were just thoughts in the experimenters' heads. They both went into the experiment. Their thoughts had nothing to do with the experiment. The experiment happened regardless of what their thoughts were. The experiment stopped at the same time that they both agreed to. And it didn't affect the data at all. And so this was where the likelihood principle was first came around. It was examples such as this, which said, why should thoughts in an experimenter's head that have no impact on the experiment or the data affect the answer? So that was the origins of the likelihood principle. And just finally, the second part of the likelihood principle says that the likelihood functions for scientists 1 and 2 are given here. They're clearly proportional. And so the likelihood principle would say that the evidence about theta from either viewpoint should be the same. So any questions on that one? Comments? Outrage? Okay, moving on. Another, I'm calling this the Jeffreys-Lindley paradox. That's its usual title. I could have cut out a counterexample, but I'm not sure what it's a counterexample to. I mean, it could be a counterexample against frequentists. It could be a counterexample against Bayesians. It could be a counterexample against both of them. So let's just call it a paradox instead. And the paradox is just basically that in testing with very large sample sizes, a frequentist can think that there is overwhelming evidence against the null hypothesis, while a Bayesian thinks there is overwhelming evidence in favor of the null hypothesis. So let me not show this. Well, we will see it mathematically. We will see it mathematically in one of my favorite examples. And the only example I've ever seen that's actually where I could say the the conditions of the Jeffreys-Lindley paradox are satisfied. And this is an example of testing for psychokinesis. Do people have ability to affect objects with their thoughts? Can I make this red pen scoot over there by just staring at it and say, move? Okay. So back in 1987, some people created a very clever experiment using electronic and quantum mechanical random event generators with visual feedback. And the subject was supposed to try to influence this generator. Here's a toy kind of picture of what was going on. There's going to be a stream of particles coming into a quantum gate. And quantum mechanics says that 50% will go that way and 50% will go that way. And these go and impact a light, turn on the light. Okay, so red or green. And then here's your subject who's mentally trying to make the particles go to the red light. Now, why do I say this is really clever? Well, you know, it's kind of outrageous to think that, okay, I can move that with my mind. But on the other hand, here you have a particle coming into a quantum gate. It's 50-50. I mean, it's just, you know, it takes almost no energy to shift that a bit. So if there is a psychokinetic ability, this would be the perfect experiment to try to detect it. All right. Now, you can model this in different ways, but let's just look at the simplest model, saying that each particle is a Bernoulli observation. Red is 1, green is 0. Let's call theta the probability of a 1, the probability you've gone to the red light. So why I said this is the only example I've seen where you're in the domain of the Jeffreys-Lindley paradox is because there were 104,490,000 particles, trials. So it is large samples, large sample size. If you let x be the number of successes, x is binomial n theta, x equal, so the actual observation was x was 52,263,470. So now we want to test null hypothesis, theta equals a half. The subject has no influence versus theta not equal to a half, subject has an influence. And you can compute the p-value corresponding to this x, and it's 0.0003. So papers were published saying this experiment showed strong evidence in favor of psychokinesis. It was actually a very well done experiment. They did all sorts of control runs without the subject staring at it, just with the particles, and sure enough, it was always 50-50. So it was a very well done experiment. I got a call one day from Bill Jeffreys. He was an astronomer at UT. Actually, he was chair of the astronomy department, and he had been on a committee that went to investigate this experiment and to find out what was wrong, because nobody believed nobody really believed that there was a psychokinetic effect. But they could find nothing wrong with the experiment at all. And he called me and said, somebody suggested that Bayesian analysis might have something different to say about this. And I said, yeah, probably. And then I told him how to do the Bayesian analysis, and he then wrote a paper on it. Now, one way Bayesian analysis could affect it is you could say the probability of H1, the probability that there is psychokinesis, you can just make it really low. I mean, a Bayesian can always do that, and I would if I was doing a subjective analysis. But that would not have provided anything counter to the evidence from the p-value. So he did what you could call the standard objective Bayesian analysis, which is to give each hypothesis prior probability a half. And then theta was the probability of a success, probability of going to the red light, and then just assigning that a uniform distribution. We'll come back to that in a minute, that assumption. In any case, computation yields under that prior that the probability of the null hypothesis, given the data, is 0.92. That's pretty strong evidence for a Bayesian. So a Bayesian says, I strongly believe that the null hypothesis is true based on the data, whereas the classical statistician says, I think there's strongly significant evidence against the null hypothesis. So there's the Jeffreys-Lindley paradox in an example. The posterior density on the alternative turns out to be a beta distribution. And here's how I like to graph these things, or I like to present these in a picture. This is the posterior distribution. There's probability 0.92 sitting on top of the null hypothesis of a half. Then there's probability 0.08 spread out elsewhere. And it's actually separated from the null hypothesis. The mass over here is almost zero. So it's quite separated. I mean, not a big effect, but it's separated. So it's either the null is true or it's over here. And that's often kind of typical in this kind of picture. Now, the trouble here, the main trouble with this analysis is choice of the uniform prior on H1 is highly questionable. You know, why? If theta could be near 1 here, if somebody's making all of the particles go to the red light, then this is such a strong psychokinetic effect that that person probably could have been able to move that down the whiteboard. This prior should probably only be looking at small theta near a half. And you can do that, and it's been done. A robust Bayesian analysis would consider a prior like a uniform on theta 1/2 minus r to 1/2 plus r, where r could be interpreted as the largest change in success probability that you would expect, given that psychokinesis exists. One can then study this as a function of r, look at lower bounds, look at the lower bounds on the Bayes factors and stuff like this is like what a lot of you do here with, well, what are your things called again? I forget them. I can never remember the name. I forgot the name. I remember what they are. I just don't remember the name. I'm old. I forget names. No, not the non-local prior, the function. Bayes factor function, right. Yeah, that also looks at curves like this with lower bounds and stuff like that. But I'm not going to show you that because, I mean, it's interesting, but it would go too far afield. I just wanted to show you an example, a real example of the Jeffreys-Lindley paradox. And I'm not drawing any conclusion from it, by the way. You know, I'm just showing it to you. Okay, here's a result that appeared in a paper by Vogt in 1993, and it's a counterexample to interpreting p-values as error rates. So a proper p-value satisfies. Oh, there's a clock. Good. A proper the definition of being a proper p-value is that if you look at the p-value as a function of the data, and if you look at it as a function of random data, then p of x under the null hypothesis is uniform on 0, 1. Volk said, let's test this versus the alternative that p has a beta 1b distribution, b bigger than 1. I'll say why he did this in a second, but let's just complete his theorem. Letting b01 denote the Bayes factor of h0 to h1. b01 is easy to compute. I mean, it's just a likelihood ratio. So it's 1 under the null, and under the alternative is this beta. So here's the beta density. And then just using calculus, Vogt showed that this, no matter what b is, this is greater than or equal to minus EP log p, when p is reasonably small. Okay, so he chose this class of distributions because it's sort of natural, because p-values should be decreasing in p under the alternative. If the alternative is true, large p should be unlikely, and small p should be likely. So you definitely want this distribution of p under the alternative to be decreasing And this is the simplest class of functions for which it is. In a later paper with Tom Selke and Susie Bayari, we greatly generalized this, and we showed that this same lower bound holds. And there's a condition that minus log p has a non-increasing failure rate, which doesn't cover absolutely every possible distribution for p, but it covers a huge number of them, a very large non-parametric class that sort of makes sense. So that this bound holds very generally, comparing p-values and Bayes factors. There's another theory called conditional type 1 frequentist error theory, which I'm not going to describe, but it is actually a conditional frequentist thing. So it's a real frequentist error rate. It's just conditional on a statistic, but I'm not going to tell you what the statistic is. And applying the same argument to that shows that the conditional frequentist type 1 error is greater than or equal to this function of p. Now, okay, those are interesting, but what's really interesting is when you look at what these bounds are for various p. So for p equals 0.05, this bound is 0.409. So remember, this is saying that the Bayes factor of the null to the alternative is larger than that, which is 0.409. 0.409, if you think of it in odds, it would be like 1 to 2.5 odds in favor of the alternative. So the Bayesian odds in favor of the alternative are at most 2.5 to 1, 2.5 to 1 in favor of the alternative. It can't be any more than 2.5 to 1. If you think in terms of frequentist conditional type 1 error, the error can't be any less than 0.289, the real conditional frequentist error. So when people first see these numbers, they're kind of shocked because people are used to thinking 0.05 is significant evidence. But when you look at what it means in terms of bounds on Bayes factors or conditional type 1 error probabilities, 0.05 doesn't mean much. Even if you go to 0.001, the bound on the Bayes factor is, 0.01. The bound on the Bayes factor is 0.123. So that means the evidence in favor of the alternative is at most 8 to 1. And the conditional frequentist error is at least 0.111, and so forth. So this kind of shows that p-values are much too small, often by orders of magnitude, to have any interpretation as error probabilities. Now I've given this example many times before in other talks, and somebody always, if not during the talk, at the end of it, comes up to me and says, "Why do you keep showing this? Everybody knows that p-values and error probabilities are completely different." So this example has no impact. I ran across, so I'm calling this a counterexample to non-statisticians understanding p-values. I think statisticians, by and large, do understand the difference between p-values and error probabilities and Bayes factors. It's non-statisticians that I worry about. And I ran across a survey that was done 50 years ago by Diamond and Forster. And I quote from the article: "What would you conclude if a properly conducted randomized clinical trial of a treatment was reported to have resulted in a beneficial response, p less than 0.05? And then here's some answers. I mean, some of these are frequentist answers, some of these are Bayesian answers, some of these are, I don't know, whatever, various answers. And then none of the above. And then they go on to say, we asked this question of 24 physicians in the Cedars-Sinai Medical Center who had been heavily involved with clinical trials and p-values and encountered p-values all the time in their work. We asked that of these 24 physicians, half of the physicians answered incorrectly, and all had difficulty distinguishing the subtle differences between the choices. Now, I mean, this is not surprising. And the article, it's really a brilliant article because it goes on to discuss, what p-values really mean, what they don't, how physicians should think about them. It's an article that's really, really good. And so I'm reading the whole article because it's really good. And then I come to the end and it says the correct answer to our test question then is 3. Okay, let's look at 3. The chances are less than 5% of having obtained the observed response if the therapy is not effective. Okay, so that's conditioning on the null. The therapy is not effective, that's fine. And they're talking about the observed response. But they say that this is the chances of having obtained the observed response. And the p-value is not the probability of the observed response, it's the tail area. So what I love about this is the people doing the survey set out to show that their colleagues did not understand what a p-value was, and they themselves did not understand what a p-value was. So I find it discomforting well, I just find it discomforting. Okay, any questions, comments about that? All right, charging along. Now a completely different scenario, shrinkage estimation. So shrinkage estimation is all over statistics today, and everybody's doing it one way or another. How did that get started? Well, I mean, you can go back into the animal breeding literature and the insurance literature, actuaries, and you can find shrinkage estimation being done. But it was not widely known in the statistical community until the paper of James and Stein. So what they did is they just looked at the situation where you have independent xi. Each xi comes with a different mean, theta I, common variance 1. And you want to estimate the vector of thetas with an estimator that depends, and the estimator the estimate for theta 1 can depend on all of the x's, not just x1. So each of the estimates can depend on all of the x's. That's the notation. And they did it under squared error, expected squared error loss. So you look at the sum over each of you look at the distance, the squared distance between each estimate and theta I, sum them up, and then you take the expectation over the data. This is a purely frequentist result over the distribution of the data. And until 1961, everybody said delta x equals x is just fine. It was the maximum likelihood estimator, the best and biased estimator, the fiducial estimator, the invariant estimator, the objective Bayes estimator, on and on and on. It was everything. Unfortunately, it was also inadmissible. James and Stein shocked statistics by showing that this estimator, which shrinks, this is the shrinkage factor. You take x and you shrink it towards 0 by this factor. And they show that it has smaller expected loss for all theta. Uniformly in theta, the expected loss of this estimator is smaller than the expected loss of x. And I'm not going to say anything more about it. It was just a highly impactful counterexample. It led to lots of new areas of statistics. While unintended, it also gave considerable impetus to hierarchical Bayes. Hierarchical Bayes had been around, as I said, but it was not terribly big back then. And all of a sudden, Bayesians were jumping up and down going, hey, this is really just like a Bayes estimator we get from doing hierarchical Bayes. And so all of a sudden, Bayesians got very interested in hierarchical Bayes. Okay. gosh, I may even finish my talk. So now here's another. I'm just kind of hopping all over the place. Although you're seeing that a lot of my examples are like coming from are like coming from 50, 60 years ago, because they were some of the most impactful counterexamples. So in 1961, Jeffreys came out with his famous book, The Theory of Probability, all about basically objective Bayesian statistics. Although he had been writing papers on this for quite a while. But to many people, Jeffreys had kind of solved the problems of being a Bayesian, namely where does the prior come from? And that was because Jeffreys had proposed a rule, which is the Jeffreys rule prior, that's automatic and could always be applied. So it's like, okay, now we have a prior, and there's justifications given for it. And so everybody was really excited, thinking that this kind of solved it for Bayesians. What the prior was is very simple. If you're given a data density, f of x given theta, you just compute the Fisher information matrix. If theta is p-dimensional, this is a p by p matrix. So you compute the Fisher information matrix. You take the determinant of it, and then you take the square root, and voila, there it is. There's the prior. So that supposedly will solve everything. Unfortunately, well, it turned out that this is great if the parameter is one-dimensional. And there have been, easily a dozen kind of independent derivations from different perspectives. That if you have a one-dimensional parameter and you want to do objective Bayes, then this Jeffreys rule prior is the thing to use. But then people started using it in high dimensions, and we're starting to wonder about it in high dimensions. Even Jeffreys himself, when he just went to the normal distribution with unknown mean and unknown variance, he didn't like the answer that this gave. So even Jeffreys himself was kind of realizing that in higher dimensions something might be off. But some things can be really off. So let me just give you two examples that show how off things can be. The first one is the Neyman-Scott problem, where here you have data. It's written kind of funny here. There's m pairs of data, m pairs of data, each pair, but there's m of them. And so here's the density. We have each pair of data come from a different mu I, but a common sigma squared. And then we have m of the different mu I. So that's the data. Neyman-Scott encountered this when they were doing a problem in astronomy in 1948. And they at first just started saying, okay, we'll solve it with maximum likelihood, the standard thing at the time. But they were really smart people, and they kind of looked at the maximum likelihood estimate of sigma squared. Now, the goal here is sigma squared is the parameter of interest. They looked at the maximum likelihood estimate of sigma squared and said, that's funny. That looks funny. They investigated it some more, and they actually found that it's inconsistent. M here was the number of stars they were looking at. And as the number of stars grew, the maximum likelihood estimate of sigma squared became inconsistent. So that's the background of this example. But it's a very good counterexample to many, many statistical philosophies that aren't quite up to snuff, including the use of the Jeffreys rule prior. So here, it's easy to compute the Jeffreys rule prior. I don't bother to show it to you. The determinant of the matrix is that. You take it to the -1/2 power. You don't care about constants in objective Bayes. So the prior turns out to be uniform in the mu's and sigma to the -m+2 in sigma. This results in a posterior density for mu that's easy to work out. Here it is, written in terms of S squared, which is the sum of squares, the residual sum of squares, whatever, and x bars, which are the averages for each pair of observations. And then we remember sigma squareds of interest. So we just integrate out all the mu I. And so these all disappear, sucking up some sigmas. And we're left with the posterior distribution for sigma squared as indicated. That's recognizable as the inverse gamma distribution, and it has mean s squared over 2m minus 2. Usually the posterior mean is what Bayesians use as an estimate. So the usual Bayesian estimate of sigma squared in the Neyman Scott example would be s squared over 2m minus 2. This estimator is also inconsistent. To see this, let sigma t squared denote the true value of the variance, and note that the frequentist mean of s squared, so I mean, inconsistency is often looked at by studying the problem from a frequentist perspective. And the expected value of s squared from a frequentist perspective over x, given the true value of the variance, is just m times sigma t squared. So by the law of large numbers, s squared over m, just divide by m, converges to sigma t squared. So the limit of the posterior mean is the limit of s squared over 2m minus 2, which is clearly s squared over m converges to sigma t squared. So s squared over 2m converges to sigma t squared over 2, which is only half the true value. Also, the posterior variance goes to 0 as m grows. So the posterior distribution contracts around the totally wrong value. And this is all the fault of the Jeffreys rule prior. It's just wrong. It's a bad prior. One more example of that, just to show you this isn't an outline case. Let's look at the multinomial problem. So suppose our data is multinomial, and we have m plus 1 cells. Theta 1 up to theta m are the cell probabilities of the first m cells. And the Jeffreys rule prior can be derived, and I just wrote it down here. And this distribution can be recognized as a Dirichlet distribution. This is the prior for theta 1 to theta m. And it can be recognized as a Dirichlet distribution with the Dirichlet parameters being a half, a half, a half, a half. And then the Dirichlet distributions are conjugate to the multinomial likelihood. So the corresponding posterior distribution is also Dirichlet. And you have in each cell, you have the cell count xi added to the prior half. And those are the parameters of the Dirichlet posterior. I just say this is problematical. And let me just look at one case. Suppose we're in the situation of sparsity. So we only have 3 observations. Okay, and we have a large number of cells. M is 1,000. We have 2 observations in cell 240, 1 observation in cell 876, and that's it because we only had 3 observations. So all of the other XIs have 0 cell counts. The posterior means, there's the formula for the posterior means, again, assuming we use the posterior mean as a Bayesian estimate. And so what do we have? We have the posterior mean for the cell probability in cell 240 turns out to be 0.005. The posterior mean for the cell probability in cell 876 turns out to be 0.003, and all the others have 0.001 as their posterior means. Well, lots can be said about this, but I'll just make one observation. This is really weird. Cell 240 has 2 of the 3 observations, but it only has posterior probability 0.005. I mean, that's crazy. And again, it's all the fault of the Jeffreys rule prior. The Jeffreys rule prior effectively starts out by giving each cell a half an observation. So the fact that it gave each cell a half an observation and gave a half an observation to 1,000 cells completely overwhelmed the data and resulted in a bad answer. So there's many other examples and that show that the Jeffreys rule prior for multinomial just isn't any good. These examples kind of came out slowly, but as they came out slowly, then everything changed. People stopped saying, okay, in objective Bayes, people stopped saying we've solved everything, we can just use the Jeffreys rule prior. It became clear we couldn't. And so then people started working in all sorts of different directions, trying to come up with different priors. I worked on reference priors, which is a way to overcome this. Mosen came up with a whole bunch of nice priors for particular situations that were good objective priors. So these counterexamples, again, within the objective Bayesian community, caused a very big shift. And my last counterexample, oh, I'm not sure I have time for it. 5? Oh. Okay, well, it's actually 6. Oh, okay. This is a counterexample to the maximum a posterior model being optimal. So up until 20 years ago or so, all you could see was people would in problems of model uncertainty, they would produce the MAP model, the maximum a posteriori model, as the answer. Let me just look at a particular regression set, and then at the end, I'll tell you the punchline. This is a very simple one, just so we can see everything clearly. The Hall regression data set had 13 observations and 4 regressors. So the full model that they posed was y is equal to an intercept plus regressing on the 4 regressors, and then a noise. And if you just consider all models here that contain the intercept, so model 134 here would be the model that has the intercept and regressors 1, 3, and 4. And I'm going to just show you the results of a model uncertainty analysis. The way it was done is irrelevant, but here's the result from the analysis. And so here's listed all the models, all the possible models. Here's the full model. Here's the null model, which consists of only the intercept. And listed are 2 things: the posterior probability of the model. You'll note that if you scan those, this model here, the model that has the intercept and x1 and x2 in it, has the highest posterior probability. So that would be the MAP model. Okay. What's given here is a measure. It's comparing the it's imagining you're going to use the model to predict future y under squared error loss, and you look at the predictive risk of using, say, this model compared to the predictive risk of using the model averaged answer, which is, for prediction, model averaging is the optimal Bayesian predictor. And you'll see this model is doing quite well compared to the model averaging answer. It only is giving up 8.19 in extra risk. But then we go over here, and we see a bunch of other models that are doing much better in terms of predictive risk, including one model 124 that has an almost zero excess predictive risk. It's essentially doing as good as the model averaged optimal model, but it's just a single model. Let's look into that a little more deeply. Posterior inclusion probabilities are important things to a Bayesian, and they are the probability that a variable should be in a model. So let's look at, let me look at P3. P3, so what's the probability that X3 is in a model? Well, we just look at all the models that have a 3 in it. This has a 3 in it. So we take that probability. This has a 3 in it. We add it to that. This has a 3 in it. We add it to that. We just add up all the ones that have a 3 in it. And that turns out the total probability of all the models that have a 3 in it is 0.43. X1 has the inclusion probability 0.95. X2 has inclusion probability 0.73, and X4 had 0.55. So the model with smallest excess predictive risk was model 124. And if you look at these, that is the model where the inclusion probabilities are bigger than a half. The only variable not put in here is X3 because its inclusion probability is less than a half. And that is the definition of the median probability model, the model whose regressors have posterior inclusion probability at least a half. And in a paper 20 years ago with Marilena Barbieri, we showed that indeed the median probability model is very often the optimal single predictive model, better than the map. So a lot of people in the Bayesian community have now, well, they still report the map, but you'll see most commonly they report the map and then they also report the median probability model. Often they're very close to each other, sometimes they're radically different. And when they're radically different, the median probability model is virtually always better. And that's it. Thanks for your attention.